Hello everyone, my name is Daniel Elliott and welcome to this video on how I came up with this volumetric raymarching. So what we have here is a 3D volume texture and we're raymarching through that volume texture to accumulate a density value that we show for each pixel. But we also have a shadow map which is being updated as well live. So we're doing a separate pre-raymarch and updating the shadow value which is then sampled in the main shader. So what I would say is if you want to get into volumetric rendering, the best place to start is probably this blog post by Ryan Bruck. Ryan works at Epic and he's a technical artist, and he's written this wonderful post talking about the maths behind volumes and how light is kind of calculated, and goes into a lot of the technical details about how to do that, like the practical steps and some of the issues that you face when doing ray tracing, that kind of thing, or raymarching. So yeah, have a really good read through this. The work that I've been doing is kind of based on this. So let's go through the scene and I'll show you what is actually happening here. So what I've got is a blueprint with all it contains is a Niagara system and a static mesh, which is a cube. So if I open up this static mesh, come up here, then coming to wireframe, it's just a cube, nothing special there. And that's the way that Ryan has kind of described how he renders his volumes, and it also allows you to kind of go inside the volume as well if you invert the normals, which is quite a nice little trick. So what we have, is this cube with a shader on it, and this shader is responsible for the final pixel value. And what it does is it takes the camera sort of location and also the intersection of like the camera ray that fires from the pixel with the box, and calculates kind of like an output location, and the difference between those 2 points is the ray that you kind of traverse through the cube. And you can kind of see it here. So you get this kind of start point and an end point, and you kind of ray trace through. But that just does the kind of the surface of the box. It doesn't do the shadows itself. So the shadows themselves are sampled in the shader. So what you see here is literally the shader that Ryan has described in kind of node form. So there's this kind of loop where you're tracing through and sampling the texture. And things have actually gone a bit further since this blog post was made, because now instead of this studio volume texture, you actually have a direct sample into the volume itself. And I'll show you that as well in a minute. But you basically loop through, sample the texture, and your final pixel value is like the value that you put onto that cube. But the shadows, let's go back to here, they are a separate texture. So if we have this texture here being piped in, that's being sampled inside. So it's a bit hard to see here. Maybe if I copy this and put it into VS Code. Just close this. And if I make this bigger, then what I have is a separate shadow texture being sampled for that kind of location in space. And that shadow texture is actually being generated in Niagara. So if I go to the blueprint here, I have a Niagara system, and you can see that the shadows kind of being updated in real time every frame. We have a render target, which can actually be set by the blueprint. It could just live inside the it could be created by the Niagara system, but I've got it set as a parameter so that we could have like per object shadows. Because if I duplicate that whole blueprint, then it's going to be using, well, it will create a separate blueprint, basically. Let me see if I can jump into this quickly. I'm kind of jumping around here, but hopefully you're following. This is not prepared. This is just me rambling. So yeah, I'm creating a render target per sort of blueprint instance, and then setting that as a dynamic parameter on material, and also in the Niagara, so that we have we're telling Niagara which render target to write into. But let's go back and look at this Niagara system. So this is the render target, and it's being used as a parameter. So here's how you kind of do that. It's there's an example in the content examples map, or the content examples level, where it shows you how to set up this as a parameter, and it's basically a parameter on the system itself that you can set from the outside, and you use blueprints to do that. But then yeah, we're kind of using that to set up this attribute on the emitter. And we also have this grid 3D collection, which is we're going to be kind of copying the data from that render target, which is actually the we're going to be sampling from that 3D texture into this grid. So we're just setting up the grids here, and then further down, what we've got in this module is, if we dive inside here, we have our texture. So we set that to be our 3D texture, and I'll show you how that's created in a minute as well. But we're just telling it which asset here is the texture, and this could be set by blueprints as well. If you had like a dynamic system where you had to choose the volume, kind of depending on gameplay, you would use the blueprint to set this, and it would be a parameter as well on the system. But we also have this grid 3D collection, which we're kind of reading into the module, and this is the one that's on the on the emitter. So what we do here is, let's move these out of the way because we haven't got enough space. We are just sampling the texture and putting it into this density channel in the grid 3D collection. So this grid 3D is just a single float channel, and we're just literally copying in the data from that texture, that 3D texture, into the grid 3D collection. Just make sure I'm still recording. Yeah. Okay, so in the next simulation stage, what we're doing is, this is where we are calculating the shadow for that. Actually, don't need that viewport because I'm not actually rendering anything. But we're reading in a light vector and how many steps we want to trace for that shadow. And what we're actually doing is, instead of tracing from like the surface of the cube and going through from the camera vector, what we're doing is we're starting from like within the 3D texture, each voxel, or conceptual voxel within the grid, we're starting from that position and we're tracing out towards the light. So what we're doing is we're sampling the density inside out. So this is like opposite, it's kind of inverted from when you do Raymarching, where you start from the outside and go through. What we're doing is we're starting in, going out and accumulating how much light ends up at that location. So this section here is how you do sort of ray box intersection. So the actual value we're starting at, if I try and find it, is we get the unit, the execution index, and that's going to be and when we transform that to unit, that gives you like a UVW location within that sort of grid 3D, which is a cube as well. It's what everything. If we keep everything a cube, everything kind of like lines up and matches in space, in local space. So this kind of 0 to 1 3D vector is the location within that cube. And what we do is we have a light vector, which we kind of transform into sort of that local space, and actually it's already in local space. This would be a parameter that we set on the Niagara system, which would be that inverted light vector, because if we have a world space vector, we need to transform it into that kind of local grid space, so that when we do this ray intersection, we get the right kind of intersection direction. And then we calculate like where that ray is kind of exiting on the cube, and we exit that position and we subtract that to get that kind of vector from the voxel to the kind of edge of the box where it would intersect. And then we do this little loop where we loop through and we sample the density at each step. and we're basically finding out how much light or transmittance is kind of is occurring at that voxel, and then we also add this kind of little bit of a rand thing, which adds a bit of dither, which I'll probably hopefully be able to show soon. Yeah, that's that stage. So we've got this sort of shadow value now, and what we do is we write that out to the render target. So this is just the mechanics. It's all a bit of a mess because I've been prototyping this. It's actually, yeah, this one up here. So we're just literally just sampling that that value and sticking it into a render target, which means we're going to be able to use that render target in the main material. So that's all this is doing. It's literally just sampling the texture, doing this quick loop with, you know, with an extra bit of maths to work out the intersection, and then it's writing it out to the render target. So nothing too crazy, but what it means is that the shadows now are a lot faster. So if I come up here, Ryan talks about this, where he says that this method is quite the previous method in the shader shown here is expensive because it Raymarches through in the main shader, and for each Raymarch it does its own internal Raymarch. So we have this kind of n Raymarches for the density kind of accumulation, and then we have m times Raymarches for the shadow density accumulation. So this one here, this yellow one, that's what I'm doing as a kind of a upfront pre-step in the Niagara system, and that bakes it out to a texture. So instead of n times m sort of rays that we're kind of, or marches that we're evaluating, it becomes n plus m, which is a lot cheaper. So the difference is that your sort of main pass Raymarching and your shadow Raymarching, they don't line up in position. So your shadow map is kind of a preset resolution that you decide up front what that is, depending on how much quality you want. And then as you're marching through, you sample that kind of pre-made shadow, and it interpolates between the voxels basically, so that you get, you know, an approximate shadow. It's not exactly the same, but a lot more faster. And you can do things like that random thing to kind of give it some dithering so it doesn't look so bad. Okay, so let's go back into Unreal. So we've got that, that's where the shadow pass is red, and then in here, yeah, in that shader, that's where we sample it. And the actual Raymarch itself is pretty much just like the one in Ryan's blog post, where we're doing the transmittance and that kind of thing, and we've output the final pixel value. So the fact that we are doing that pre-shadow pass means that I'm recording, so I think it's locking up and being quite slow. Here we go. So yeah, we're sampling that shadow. The actual main texture is coming in through this texture object, and I'll show you now how that was created, because it's actually quite nice how Houdini ships with this set of tools, which you're probably aware of, but if you're not, there's this Side Effects Labs tools, which if you come up to the shelf and you hit plus, you can go to shelves, Side Effects Labs, and then there's an option on here to update the toolset, which will give you the latest versions of these. But there's a really cool tool on here called VDB Textures, and what I've done is I've created just a bit of test geometry using the pig head. I've converted that to a VDB, and I made sure to make it a density volume, not a distance field, and then just ran it through some cloud noise just to give it some, nice looking displacement. And then in the volume texture, this literally just by default this preview checkbox is off. So this volume texture inside of it has all this kind of mechanics for working out how to lay this out as a sprite sheet. and you basically set the resolution, and what it will do is dynamically kind of update these parameters. So you say resolution, it should work out those dynamically. And if you preview, then what you get is why is that not working? Okay, use the little drop down to set a resolution, and it will update it then. So it's better to use the presets here, because I think there's some kind of callback to set these. And what will happen is it will render out this EXR file, which you're then able to import directly into Unreal as a volume texture. So if I go to this texture now, you'll see that the actual type itself is a 3D volume texture, and it allows you to preview this as slices as well. I can't remember where the option is for displaying as a 3D volume, but there is a way to do that. View settings, trace into volume, use your mouse to zoom in here, and there's also you want to turn on the channel that you want to trace into. Oh, I can't remember. Sorry about that. I will come back and show that in another video, but yeah, this is how you import into Unreal as a 3D texture, and then you can actually use that as an asset in your shaders, which is quite cool. So let's go into some of the more specific details about this blog post. We have this step where Ryan talks about these kind of slicing artifacts because of the way that you calculate your start positions and end positions. Where's that nice image? Yeah, here. So if you calculate the box intersection this way, then the rays are kind of always going to be offset by this kind of constant amount, and when viewing at it from a certain angle, they kind of display this kind of like slicing artifact. Whereas if you change those positions to be at the same kind of like distance from the camera, then it ends up behaving like a series of planes, and you can drastically reduce those artifacts. And that also means that you have to do this kind of extra step as well to account for like that little bit at the beginning and also a little bit at the end, where you'd get the same thing, where there would be a bit of extra volume that you would need to kind of accumulate, which yeah, you there is a little bit of code here which shows that. I can't remember where that is. I think he just mentions it here, but there's also a YouTube video where he talks about this, but this is done in the main shader, and that's done up here, I think, where I'm basically figuring out this kind of extra step to do and adding it on, and that's kind of a final step that we do. And all of this stuff here, which looks like a complete mess, it's kind of very carefully calculating those distances based on the step size. And this magic value, this 1.732, that's the length of the diagonal of a cube. So if you start from kind of the top left corner and end up in the kind of the bottom right corner, that distance is this value. And that's kind of what we're doing, saying is like the maximum distance in kind of local cube space that any vector could be, and we base all of the kind of the other sort of step sizes, sort of they're all kind of normalized against that basically, so that we know how many steps to kind of step through. So even at the corner of the box, we know how many to do and how many extra steps to do. So it's all a bit hard to understand, like when it's laid out like this, but it was a fun experiment to kind of go through and do it with nodes as opposed to doing it all in one big expression. this could probably be broken down into little material functions, and that's something I probably might try soon, is just to kind of try and make all of this a bit easier to understand, because no one likes seeing spaghetti mess. But yeah, you can kind of see these like plane offset stuff. There's a lot of stuff going on here, but it works. Let me try and see if I can show the so if I turn off this plane alignment and stick it to 0, does that show the artifact very well or not? No, it's not showing it very well, but anyway. Yeah, I don't think there's too much else to show here. There's some more things I want to try and do, like improve some of this kind of when I go inside the volume, and that is due to that final step not being calculated, I think. I'm doing it from outside the box and you don't really see it, but when you go inside there is an extra bit of density that needs to be accounted for. But yeah, have the shadows updated in one straight pass, and then the main shader can use that shadows. That's the main benefit of this approach. So yeah, I will just leave it there, and what I'm going to because the whole point of this shader was that I wanted to be able to see a 3D fluid simulation. So now I have this, I can actually use it as a way to actually look at it. So yeah, thank you for watching. Post any questions you have in the comments and I'll try and get back to you. Or you can find me on Twitter. If you just look for at Daniel Elliott 3D, that's me. That's my ugly mug. And yeah, I'm on here quite a lot, so feel free to ask me stuff, chat to me, and I'll get back to you. Thanks very much for watching.